All right. What I'm now going to introduce is a new circuit. It's called the Wheatstone bridge. Does that ring any bells from 204? It does. Okay, so let's, someone was like, yeah, but someone was like, I'm not, and that's right. I think that's the correct approach to, so let's draw what the Wheatstone bridge is. But I want you to remember that whereas in circuits, you solve circuits because you need to solve circuits, here we only care about circuits to the extent it makes our life easier to make better instruments. So that's the focus here. The Wheatstone bridge is a circuit that looks like this. We still have a battery, let's just call it E, of some voltage. And we have 4 resistors. Let's do R1, R2, R3, and R4. And the voltage output, we'll call it V out, is measured from here to here, right? That means that our multimeter is being positioned here. So let us review what you know about this from circuits, and then let me show you why it is a nice thing to use in instrumentation. In instrumentation, the only reason we would add complexity is because there has to be a good reason. I'm going to give you that reason. But let's review what it is. Now, one way to look at a Wheatstone bridge is to cover up this side of the circuit and see what's left over. And then we'll repeat it for the other side. If you cover this up, what you see is that there's a voltage source, and these resistors are in series, right? But more so than that, it's the same circuit. It's the same circuit. You can say, but I think one of the reasons, I still remember seeing this as an undergrad, and one of the reasons it initially intimidated me is like, well, there's these angles. Why? Like it's like a cube? Forget the cube. That's just a nice way to draw it, right? You don't have to draw it that way, right? This is just a voltage divider. And this is another voltage divider. So let's start by writing V1 here and V2 here, and let me solve what V1 is in terms of a voltage divider, and then I'll do the same thing for V2. Now here's the thing. I am allowed to put my hands over parts of the circuit and solve just the part I'm interested in. You are not. We'll talk later today about why, as a general rule, you cannot do that in circuit analysis. If you have a circuit like a resistive network, you're not allowed to not look at certain parts and solve other parts and then go back, okay? It happens to actually work out in this case. All right, but as a general rule, you can't do this and this. It does work out in this case. So let's do it. Let's write the equation first for V1, which is the voltage divider equation, which is V1 is equal to E times R sub 2 over R sub 2 plus R sub 1. That's the voltage divider here, and R sub 2 is on the top, right? Because we're measuring, right, in the voltage divider. So this is going to be our reference. So we're measuring here to be, sorry, that wasn't clear. V1 is from here to here, so we're measuring across V2, which is the RA, right? You want to be careful about that. V2 is also measured from here to here. Ignore the negative sign for now. The negative sign only mattered when we measured from here to here. But now we're just back to a voltage divider, and we're measuring the voltage from here to here. So that's going to be V sub 2 is equal to E times, well, I did it this way, fine, R sub 4 over R sub 4 plus R sub 3. Now, V out is equal to V1 minus V2. You can say, does that mean you're actually subtracting something? I wouldn't think of it that way. I would think of a voltage as always being measured between 2 points. Right? A voltage is, it's like height. There's no height without reference, right? So maybe we weren't, this was always this voltage, right? And there was a voltage here. So this voltage is simply going to be the voltage from here to here, and so we're going to write that as V1 minus V2, right? You could, and let's leave it at that. We could have done V1 minus reference minus V2 minus reference, but the reference would have dropped out, okay? Okay, and so now, well, we have everything we need, so therefore V out is equal to E times R2 over R sub 2 plus R sub 1 minus, because this is where the minus comes in, R sub 4 over R sub 4 plus R sub 3. And there we have the equation for the Wheatstone bridge. This has yet to explain why, in this class, you would be very motivated to implement Wheatstone bridges, right? That has yet to be done. So that's what I'm going to do next. But I want to get first some intuition about the Wheatstone bridge. Just to get, right? Just to get some, yes?
Why is V out the difference of V1 and 2 and not their sum?
When you measure the voltage between two positions, right, it's always this voltage relative to that one. So it's the minus, like, how to make it more intuitive than that? If I taken the voltmeter and swapped it the other way around, I would be measuring V2 minus V1. It's like if I put a voltmeter here, positive terminal, negative terminal, I might measure 9 volts. And if I go here, it's minus 9 volts. But I wouldn't do 9 plus 9. It's just measuring from here to here. Yeah, but okay. I want to go through, let's say, a couple simple examples. Let's say that all the resistances are 1 ohm. So that means that R1 equals R2 equals R3 equals R4 equals 1 ohm. And let's give E a value too. I'm going to give E a value of 10 volts. Let's first think about it from this perspective, and then we'll jump here. So in this case, we're going to have 1 over 1 plus 1, which is a half, times 10 volts, so half of 10 volts. So therefore, V1 in this case is equal to 5 volts. And V2 is also equal to 5 volts because it's the exact same thing, 1 over 1 plus 1 times 10. From a voltage divider perspective, you remember that these resistances divide the voltage, and they divide the voltage according to their resistances. But if these resistances are equal, they will divide the voltage equally, which is why you see for a 10 volts, when these are equal, you get 5 and 5, right? So that's what you're seeing here, just to get that intuition, 5 and 5. However, V out is going to be 5 minus 5. So V out is actually 0 volts in this case. So if we have 1, 1, 1, and 1, and we measure here, we measure nothing. Because this voltage divider and this voltage divider are actually doing the same thing. They both went to 5 volts. All right? Now, if this was not the case, of course, we would see something else. So let's go. I want to work through these examples. Let's change R sub 2. So R sub 2 is equal to 2 ohms. However, the rest, R sub 1 is equal to R sub 3 is equal to R sub 4 is equal to 1 ohms. Let's see what happens in this case, right? So on this side of the equation, nothing has changed, right? On this side of the equation, nothing has changed, right? Because this remains 1 and 1, right? So we know that so we know that V2 is still equal to 5 volts. However, V1 is no longer equal to that because now we have 1, right, over 1, right, plus 2, so 1/3. So we're going to go to roughly, and then 2 over 1 plus 2, right? So we have 2/3 times 10 volts. So we're going to be at roughly 6.7 volts. 6.7 volts from here to here, 5 volts from here to here. So the difference between these potentials, okay, is that this potential is 1.7 volts greater than this potential. Where we're to measure from here to here, right, which is getting back to your question you asked earlier, V out is equal to V1 minus V2, which is equal to 1.7 volts. So by this resistor changing, we now, by changing this resistance, whereas before we measured 0, now we measure 1.7. I'm getting here, something that you do care about, okay, as we continue to work on it. I want to go through yet another example. Now what I want to do is I want to take R3 and I want to change it. I want to make R3 into 2 ohms, and I want to leave the rest, R1 equals R2 equals R4 equals 1 ohm. What do we do in this case? Well, on this side of the equation here, right, I've restored balance, right? I'm back to 1 and 1, right? I'm back to 1 and 1, right? So 1 and 1 makes this 5. All right, so, and to be clear, the volt, in all these cases, I didn't change their battery, right? I didn't change the battery. So now I'm going to go back to V1, and V1 is equal to 5 volts. What about V2? Well, now we're looking at this side. Now I've changed this one here, right? Now remember, we're measuring the voltage across this one, right? So we're going to get, this one hasn't changed, 1 over 1 plus 2, 1/3. So V2 in this case is going to be 1/3 of 10 volts, or roughly 3.3 volts. You can say, wait, why did this one go up and why did this one go down? Well, I did something subtle. In the first example, I made this one go from 1 to 2 ohms, right? But in the second example, I made this one go from 1 to 2 ohms, right? So this other relationship happened. And finally, we can ask, what is V out? Well, V out, as always, is V1 minus V2, right? So in this case, we're going to get 2, did I do this right? V1 minus V2. Yeah, 2.7 volts. Right? 1.7 volts, thank you. 1. One final example to complete it out. I now want to make both these changes happen, right? I want to make both these changes happen. So now I'm going to say, and I promise this is the last example before I explain why you care about this for instrumentation, right? I'm going to take R3 and I'm going to take R2 and make them into 2 ohms. And I will not touch R1 and R4 to leave them as 1 ohm. So what happens in this case? Well, we actually have a situation where we have V1 is equal to 6.7 volts, and V2 is equal to 3.3 volts. How did I do that so quickly? Well, V1 was impacted by R2, right? And V2 is impacted only by, what do I do here? R1, R2, oh, no, this is fine. Yeah, right here, sorry. So we essentially reproduced what was happening on the moving side in both cases. And therefore, we get V out is once again equal to V1 minus V2. Now, what's this difference now? Now this difference is 3.4 volts. Oh, okay, so that's different. Sorry, and this is where I wanted to go. Who cares, right? Up to now, this feels like circuits, right? We have a situation where we had 0, 1.7, 1%, and 3.4, and these different voltages reflected different values of what was going on here. Now let me make it about instrumentation.